Lesson 6-4, graphing radical functions. So we're going to make a lot of graphs. The radicals, they mostly focus on two kinds of functions, which are square roots and cube roots. So here to show you guys a blown up version of that, I have this queued up on Desmos. Let's look at some basic shapes here. Here's y equals the square root of x. So here if I zoom in a little bit, square root of 0 is 0. Square root of 4 is 2. That's that point right there. Square root of 9, let's see, should be 3. That's right about there. Yeah, that's about right. Okay. And then cube roots. Let's look at that. Now, how I'm going to type cube roots in the calculator is I'm going to raise it to the power of 1/3. You guys remember that? Power 1/3 is the same thing as a cube root. I could have done a similar thing with square root. I could have done to the power 1/2 and then cube root power 1/3, right? But hey, look at the shape. So the cube root of 0 is 0. That's to say if you go the other way around, 0 to the power of 3, 0 times 0 times 0 is still 0, right? What about how about what's the cube root of 8, right? Which I'm pointing to it right about here, right? It should be like 2, shouldn't it? Because 2 times 2 times 2 is 8, right? So I think the point 8 comma 2 is right there. But hey, look, cube roots do something that square roots don't. They can go to negative territory. So the cube root of -8 could be -2, right? Because -2 times -2 times -2 would be -8, right? Whereas square roots, well, there's a domain restriction, right? Because you can't take the square root of a negative value to get a real answer or to get a real number. Maybe complex or imaginary you could consider, but not real values. All right. All right. So here, now let's get a good look at this right here. And what is the book going to have us do next with these is to look at um, um, features of the graph. So here's the square root of x I was just showing you guys. Right, so domain could be x could be greater than or equal to 0. The range could also be greater than or equal to 0. Right, remember, domain is possible x values, range is possible y values. So for these square roots, there's that domain and range restriction. Intercepts, well, there's only one. It's at 0, 0, just touches that point. Okay, that accounts for both x and y intercept. In behavior, as x goes to 0, f of x also goes to 0, so it approaches this endpoint here. But then go the other way. When x approaches infinity, if you go infinitely far to the right, f of x also approaches infinity. Like if you take square roots of bigger numbers, you just keep getting bigger numbers. It doesn't asymptotically approach anything. Uh, Increasing, decreasing. Well, this function is always increasing as long as x is greater than 0. So if you start at x is 0, right, and you move to the right, right? So if they ever say something increasing or decreasing, your default assumption is that you have somebody walking left to right. And yeah, they'll always be walking uphill. So this would always be an increasing function. Has a minimum at 0, 0. It has a positive values where x is positive. Right? There are no negative values anywhere. Notice that. Right? No negative values. Everything's positive. X's are positive. Y's are positive. Right? And is there any kind of symmetry? Well, no. Right? There's no line I can introduce, horizontal, vertical, or otherwise, that you can flip it around like a mirror. Also, I remember there was that point symmetry. I think they call that odd functions back in the day. That doesn't exist either. Right, so nothing like that. Okay, so we just went through this, all of us. Right, that's nice. Right? All right, and then this part right here. We say, hey, what if we shift this around, stretch it, shift it around? I wrote this here a lot bigger, something like this. Right? So if the parent function is just f equals the square root of x, right? So x is your independent variable and f of x or y could be your dependent. Okay, that's what the shape is here. I just showed you on Deathmouse, right? But how do you shift this around, right? So here, your book focuses on three ways to shift this around. Okay? So if you do minus h inside, that could shift it to the right h units. So I'll call this a horizontal shift. They might call it horizontal translation, a little fancy term, right? Notice you're always subtracting it off. So if I say -3, it shifts 3 to the right. If I say +3, that would be 3 to the left, right? Okay. Right, then plus k, well, this would be your vertical shift. Right. Notice that the function's already happened, and after we've done all the square root and all that, right, if you say plus k at the end, you can shift the whole thing up. Now this one, if it says +3, it does go up 3. If it says -3, it goes down 3. So that's a bit more intuitive. The vertical shifts are a bit more intuitive. Right? What about this a I slapped in front? I'll call that a vertical stretch. Right? You can imagine, okay, if you did the square root of x and then you just multiplied it by something after the fact, wouldn't that just like stretch the numbers vertically? Right? Regardless of whatever x you put in, right? Stretch vertically. Right? Now you could shift it to the right or to the left horizontally, right? And then still stretch it. The stretch would still be the same. Right? Okay. And then I guess the order you apply these, because they're sort of in order, I would probably do horizontal shift first, then vertical stretch. And I would definitely say the vertical shift for last. Right? That would be the last thing. Right? Now, notice what I have not actually put in here, and I'll jot it down real fast. because your book doesn't super focus on it, because there is one more stretch you can do, but it's a little trickier. It's less intuitive. So what if I had something like this? Right, so first I'll just copy down everything that's already there. Like that's all same, whatever. Okay. What if I had a value b right here? Ooh, notice here I just left it as one, but what if I had a b? Well, this would be your horizontal. I want to say stretch. I'll say slash squeeze because everything about this is well, okay. This is maybe the least intuitive one to work with. Right? So the bigger this number gets, the more it's going to squeeze your function. Right? Whereas the vertical stretch, the bigger it is, the more it stretches it vertically. But this one sort of works opposite that, squeezes it. Right? The bigger it gets. Also, notice how it's factored out of the x minus h. So it's like you've done the horizontal shift first, and then you worry about the horizontal stretch or squeeze afterwards. Right? Again, your book doesn't super focus on this. I just want to at least throw this out there, like, hey, kind of be aware of this. Maybe and it could show up in this class or Alex, or more likely in college if you take math in college. Right? You might say, okay, okay, so knocking all that out. Right here, I just basically went through this with you guys. Right? All right, so here we go. Let's jump into some examples. Example one, identify the, domain and range, algebraically, domain and range. Okay, so that's all I want you to do on this one. And then, okay, so here, I'll just do exactly what they offer. Okay, so we have f of x, I'll just say y there, equals square root 2x minus 6. And then after that, we got a plus 1. Okay. Now, this is one of the rare times that the book actually did throw a factor 2 on the x. They pretty much don't do that, or I don't remember them doing that so much later on. Yeah, looking at all these examples, they didn't really do that so much. Okay. So you could think of it like this if you wanted to, square root of 2 and then x minus 3. Okay. So really, I think if you're saying like how much has this been shifted from the parent function, where the parent is y equals the square root of x. Okay, that's like the basic graph that you could start shifting around from. Okay, I want to say this would shift to the right 3 and then up 1. Right, but don't forget it also gets squeezed horizontally by a factor of 2. Or there's one more way you could interpret this. You could take out this 2 as the square root of 2. Okay, and interpret that as a vertical stretch, which might actually be easier to work with. Okay, this would probably be the easiest form to work with. Anyway, they asked for a domain. Here, let's do it both ways. Let's answer the question first, domain, and then I'll throw this into Desmos and see what it looks like. And I'm pretty sure you should follow what I just said. Okay, so the domain restriction here is that, remember, you're not allowed to take the square root of uh, anything that's negative. If they ever ask for a domain restriction, say, well, what could restrict the domain? Usually you want to avoid dividing by 0 and avoid taking the square roots of negatives. So I know that x, so for domain, to address that question, domain, I know that the x minus 3 bit has to be greater than or equal to 0. It could be 0. It just can't be anything less than that if I want a real answer, if I don't want to go into imaginary territory. So then x would have to be greater than or equal to 3. Okay. Now this could be the answer in interval notation. If I want to write the answer in set builder, I would say domain x such that x greater than, or sorry, this is more formatting set builder. Just a fancier way to write. Sorry, interval notation would be like x could start at 3 and then go on to infinity. All right, there you go. That's all right. Here's my interval notation, and here's my set builder. Set builder. And then the sort of shorthand form of set builder could be this. And let's see, did you have a preference for that? Yeah, they went with set builder. It looks like they went with set builder. So if you're looking for this. All right. All right. Now here, I'm going to throw that into Desmos and see exactly what does that look like. All right, so there it is. Now, does that follow exactly what I said it should have? Let's see. Because I did do a few manipulations. I said this should shift from the parent function. It should shift right 3, and then you could interpret this as stretching it vertically by 1.414. That's what the square root is. Right? And then you shift the whole thing up 1. Right? Is that what this came out to be? All right, let's see. The parent function is in red. The new version is in blue. Yeah, this is to the right 3 up 1. Right? You guys see this origin point? Right 3 up 1, just like I said. And it looks like it is stretched vertically a little bit. I mean, it's kind of subtle, but you can tell. Yeah, the blue one's stretched vertically by factor of 1.414. Yeah, it looks like just like that. That is exactly what it should look like. Yeah, so we are in good company. Keep going. Example 2. Graph a transformed square root function. Okay, so kind of what we just did, but let's check this out. Okay, so we got example 2. we got a g of x equals -3 square root x plus 1, and the whole thing is plus 2. Okay. Okay, well, let's break this down. I think the first thing we do is say plus 1 inside the radical moves it to the left 1 unit. Okay. Next thing is, I'm gonna look at this negative. Oh, negative. Guys, what do you think negative does on the vertical stretch? Shouldn't it flip it upside down? I think that's exactly what it would do. So uh, vertical stretch times 3, and it's also upside down. Upside down. Ooh, because the negative. Okay. And then finally, this would be up to, right? Now they made a whole table of values, so you could always do that, right? If you're ever really stuck on what does a graph look like, you could always break out an XY table, just start plugging values in. Okay, so they did that too. Okay, let's see. Okay, so I know the parent function. Here, oh, right, the parent function is y equals the root x. That's like your basic graph. Okay, so that would have points at 0, 0. You plug in 0, square root of 0, 0, square root of 1 is 1. Square root of 4, 2, 3, 4 would be 2. Okay, I think it's going to give us the basic shape. So here's the parent function right here. Okay, this one. Okay. Now, how about this? So I'm going to go left 1. So I'll step first. That would bring me kind of over here. Okay. Then the whole thing upside down, vertical 3. So upside down would be doing something like this, vertical 3. Let's see. Instead of -1 here, I have to multiply it by 3. So that brings me down here, somewhere like this. And this would be up at 2. So -2 times 3 is -6, 3, 4, 5, 6. That's kind of here-ish. Right? So now it's like this. But one more transformation, which is you shift the whole thing up 2. So then from there, go up 2. It's that point there. This point was here. Now there. This point was here. Now there. Right here. And I'll put this in pink because pretty sure it should look just like that. Okay. Now it'll go down to the right forever. Okay. Let's see. Here, I will. Here, let's check this table. Okay. So did we get the same table values? So -1, 2. Yeah. Right. They got -1, 2 right here. So did I. Like if you plug in -1, this whole thing zeroes out and it just leaves you with 2. So that's really that point right there. -1, comma 2. Okay. I got the point 0, -1, plug in 0, square root of 1 is 1, -3 plus 2. Yeah. And yep, that's what they got too. So this point right here, point is 0, comma -1. Okay. Yes, but like the way I graphed this originally was I just followed all my shifting rules. Okay, shift this way, stretch this way. Okay. But then each individual point is coming out exactly where it would have if you just plugged it into expression in the first place. What if you plug in 4? Or no, that's not right. Because we just shift left. Okay, let's do 3. This should be 3 right here. 3. So plug in 3. 3 plus 1 is 4. Square root of 4 is 2 times 3. Okay, -6 is negative. Okay. Then plus 2 is -4. That should be this point right here at 3, comma -4. Did they get a 3, -4? Yeah, they also got a 3, -4 right there. Right. Yep, so that's it. That is it. All right, example 3. Analyze graph of a square root function. We have a word puzzle. When blood is donated, medical professionals use a centrifuge to separate it. Right, you guys seen like a centrifuge? Kind of draw up here. Supposed to put in little test tubes. Right, got some blood in here. Right, it's gonna give it a spin. Like, right, goes so fast it'll separate out everything. These are ordered to a little different. You guys get the idea. Get separated out. If you've ever been on a merry-go-round and your friend gives you a spin, it's just a little too fast, like, you feel like you're being thrown out. The centrifuge spins the blood, causing it to separate into 3 components, which are red blood cells, platelets, and plasma. To efficiently separate the blood, the centrifuge must spin at a specified rate, measured in rotations per minute, RPM. It tells you something about how to quantify how fast is it spinning, RPM, revolutions per minute, for a required gravitational force or G force exerted in the blood. For a centrifuge with a radius of 7.8 centimeters, so they give me this radius, call it radius equals 7.8 centimeters. Okay. The revolutions per minute setting of the centrifuge is determined as a product of 104.23 times the square root of the G force required. Okay, so I'll call this the spin rate. equals product of 104.23, product means multiply, and the square root of the number of g's required. Well, maybe I'll just treat that as the independent variable, number of g's, right? For example, if you're just sitting in your seat in class, you're experiencing one Earth gravity, so this value would just be one. But if you get on that merry-go-round, like you were just thinking about, your friend gives a spin, I bet you feel more than 1 g. I bet you feel a little bit heavy, maybe 1.5, 2 g's. And how about this blood? This blood might go up to, let me give some examples. Yeah, hundreds, even thousands of G's. Ooh, right, to really separate out these different components. And so this is basically the equation we're looking at. Okay. What do they want us to do with this? Graph the function and complete table and okay, domain range, all that stuff. Right. Okay, so I bet we could graph this. Let's throw some points in here. Okay. Now, since they're going up to like almost 2,000 G's, maybe we should do that too. So here's G's, number of Earth gravities, like gravity field, right? You could also quantify this in meters per second squared, would be a way to do that too, right? And then the required spin, right? Maybe like, okay, well, we got to separate out this blood this certain way. And the only way to do this, we got to get it up to 800 G's. We got to get 800 G's. And then it's up to you, maybe as a technician, to figure out, okay, well, how fast do I have to spin this? You resort to this expression and yeah, let's make a table. See a table right here. Right. So we're going up to 2,000 G's. Half that would be 1,000 G's. This would be 500 G's, 1,500 G's. Okay, let's plot some points here. So the sort of G value and the required spin rate. Okay. Okay. Spin was in RPM. Okay, so RPM. Right. Okay, so all right, calculator time. Let's go 104.23 times the square root of G. Here, I'm going to plug in my base value first. Let's see that. So go 0, 500, 1,000. Because if I plug in my base value first, I'll have an idea of like what range I should go with on this graph. Right. I think I said the number 800 earlier, so I'll throw that in there too. Okay, so we got all these values. All right, so square root of well, 0 would be 0, of course. Right. Let's go 2,000 right here. What's happening at 2,000? And it is 4,661. 4,661. I'll just round to the nearest whole value. So that's almost 5,000. So 1,000, 2,000, 3,000, 4,000, 5,000. 5,000, 0, 1,000. You guys notice how I scaled my axes linearly? Great. So I started 0, 0, and then this horizontal axis I'm going in increments of 500 each, right? My vertical axis I'm going in, I also start at 0, 0, right? And then go in increments of 2,000, or I'm sorry, 1,000 each. There you go, 3,000, 4,000, 5,000. Okay, so so this should make a square root looking curve. Right, we're gonna find out. So at this point, 2,046, so probably right about there, and 0, 0, right there. So we got those 2 points. So there's some more points in here. What if I go with 1,500? This would be 4,037. Okay, so that's a shade over 4,000. So that's probably right about there. It's pretty close. Let's go 1,000 even. Okay, everything's just up there. 3296, 3296. So that would be 30. It's probably about there. Pretty close. Let's go 500. So 500. This looks like 2331. 2331 is probably about there. And I also threw in 800, so let's do that. Okay. 2948. 2948. 29 is probably right. Right there. Okay. Stand back and look at them. Oh, yeah. Okay, so 0, 0 is the point. And then all these points. Okay, and look at that. If I connect these points, yeah, pretty well looks like some version of a square root, which it should, because that the parent function would be a square root. Yeah, that's it. Looks like that. Okay. Side note here, if you take my physics class and you actually do a bunch of those labs and get a bunch of data, this is something I see all the time, is that students will plot the data. It might look a lot like this for some of these graphs, right? And then I'll ask them what relationship are they working with. And at a glance, do you guys notice that at a glance, these points kind of look like they might be in a straight line. You know, if you're getting lab data and with high school equipment, it might be kind of hard to tell, right? But oftentimes it ends up being part of, in this case, a square root function, or you could all have the inverse case and have a part of a parabola. So that could happen too. And so things to look for in a physics class. Let's move on. Example 4. Analyze a transform square root function. Consider g of x. Okay, shown in the table. Identify the type of transformation as it relates to AH or K. Okay, so we're going to take f of x, which is the square root of x, which they also gave here, and we've been looking at a bunch of those, right? And we're going to come up with some g of x. And here, I'll write in the uh, placeholder value. Like I said, we got like an a, right, got some kind of square root. I'll do x minus h, and then the square root closes, and we'll tag on a plus k again. But we can come up with values for a, h, and k. Right? If we're looking at this table, and I'll write this table a little bit bigger so that it's easier to see too. So x and g of x. So they gave us the values 0, 1, 2, 3, 4, and 5 for x. And then for g, we got 0, 1.41, 2, 2.45, 2.83, and 3.16. Okay. You know, a lot of these have approximately equal to, so it may not be exact, but it's pretty close. And one thing that stands out to me right away is 1.41 is about the square root of 2. Now, if I look at the parent function, square root of x, and I take the square root of 1, I get 1, right? Maybe if I made an extra column for f of x, the 0.11 would exist. Um, and I don't think g of x has been shifted right or left. H and k is probably 0 and 0 because 0, 0 would also be a point on f of x. So I don't think it's been shifted around, but maybe stretched. Now you can interpret it vertically or horizontally. We're just going to stick to vertical. All right, that's all they're asking for anyway. That's the easier interpretation. Okay? I'm thinking, how do you go from 1 to the square root of 2? Well, you multiply by the square root of 2. So I already have a hunch just from these first 2 points what the answer is. I think h is 0, k is 0, and a could be the root 2. Now, I don't 100% know that for sure, so I'm going to check these other points and see does that actually check out. So, for example, what if you plug in 2? Okay. Now, if you plug into the original function, the square root of 2 is 1.414. Okay. But for g of x, it is 2. Okay. Now, is that consistent with these? Well, I'm saying basically just ignore the h and the k because those are 0, and just multiply by the root 2. Does that work? Root 2? Yeah, that worked exactly. How about these other 2 points? And so I'll just feed it in here. So square root 2. Okay, so I'm claiming that. Times, and then the square root of x. So I'll pop in a 3 right there. Right, and then everything else is just 0, 0. So just ignore that. So you get 2.45. Yeah. Right. How about I plug in 4 for x? 2.83. Oh, yeah. Right, yeah, these are all lining up. So that was exactly it. 3.16. Yeah, yeah. It all worked. It all worked. Okay. So good there. Right, cube roots. Cube roots. Okay, so this is the other graph. Let me remind you guys. I got a Desmos right here. Okay, so we've done the square roots, done that. But we're flipping over to cube root. Okay, so remember when I'm punching this in the calculator, I'm going to express this as to the power of 1/3. I just always do that. And notice how I put the 1/3 in parentheses. I definitely have to do that also in the calculator. Here's the parent function for cube root of x. Looks like that. Okay. So for example, cube root of 1 is 1, cube root of 8 is 2, cube root of 0 is 0. You can also go negative. Cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Okay, so I see all those points signed. All right, what are we going to be doing with this? Okay, they're looking for domain, range. So domain could be all real values because you can go left or right forever. Range could also be all real values because you can go up or down forever. Like, is there an x value such that the y value is a billion? Yeah, somewhere out there. Okay. Max or minimum? Well, there is no absolute max or minimum, or relative for that matter, because it never like, curves around, comes back up. Right? It just keeps going down to the left forever and up to the right forever. End behavior as x approaches infinity, f of x approaches infinity, and then negative, negative. Okay. Yeah. Now, it does have a certain kind of symmetry, though. It says symmetry about the origin. This is an odd function. Do you guys notice that? If you took f of negative x, it would be f of x. This is an odd function. It does have symmetry like about the central point, so about the origin. Okay, so example 5, graph cube root functions. All right, so they threw one at us. Want us to graph that? I guess we could make a table and graph it. Let's do that. Example 5. So we're doing a g of x, they're calling it, is 1/3 of the cube root of x. Okay. Or how I might like to think of it is 1/3 times x to the power of 1/3. Okay. Okay. Remember, these different 1/3s are doing two totally different things. Right. This 1/3 in the power is effectively a cube root. This 1/3 in the front is like a vertical squash. Just make it a lot shorter. Okay. So yeah, this tried and true method is you could come up with a table of values, see what happens. X, g of x. Okay. Now I know some good cube roots, or I should say perfect cubes. Okay. So what are some good perfect cubes? Well, one's a perfect cube. See, 2 cubed is 8. So maybe I want to play around with 8. 3 cubed is 27. I can play around with that. What's 4 cubed? 4 times 4 is 16. I think it's like 64, right? You can also go negative. So here, I'll throw in a couple of those too. How about -8 and -27? I don't know. Better. Right. So what would g of x be? Let's find out. Let's find out. Right. X, y. Okay, I better go. Okay, guys, scale this up to at least 64. Let's go 10, 20, 30, 40, 50, 60, 70. 10, 20, 30, 40, 50, 60, 70. Okay, and we're also going negative. 10, 20, 30. That would probably be good enough. Right now, ooh, how should I scale the y-axis? Okay, and I'll scale a little differently. I mean, they did give us the answer here. You guys notice how like squash this graph is? Right? So yeah, maybe just to blow it up a little bit. What if I plug in the most extreme value I have right here? Right? Like 64 to 1/3 would be 4. I know that. That's why I picked this number to start with. And then divide by 3. Well, what is 4 over 3? It's only 1.33. Right, which is really small number compared to the numbers I have here already. So I'm just going to scale the y-axis to maybe 2 at the most. 0, 1, 2, and then go the other way. Right, negative 1, -2, like that. Okay, so notice really got a squash x-axis and a really stretched out y-axis. Okay, just so you know the context there. So let's plug in some values here. I'll do here. I'll do it this magic way then show you guys. So you can just plug in the function. So I've got 1/3 plus parentheses, and then wherever you see an x, do second answer, right? Second answer, right? And then you can just very quickly swap it out later. Right, so that's the power of, and then in parentheses 1/3. Okay, so let's start with 0. Then scroll up, plug that in. Of course, I get 0. Let's do 1, plug it in, I get 1/3 or 0.33. Here, I'll say 0.33. If I plug in 8 and plug that, 0.67, 27, 1, 64, 1.33. But we did that one earlier, so you know that one. Okay. -8, I get negative 0.87. -27, I get 1. Okay, that's plenty of points right there. Let's plug them down, see what this looks like. Okay. So 0, 0, 1, 1/3, 8.67, 27, 1, 64, 4/3. Yeah, that is looking kind of like this one. Again, the book version, they scaled their x and y axis the same, so it looks really flat. Mine is stretched out a bit. Yeah, that's what it should look like. Right, -8, -0.67. Let's talk about -27, -1. Right there. Yeah, this is looking pretty good. Pretty good. There we go. It could go up to the right forever. It could go down to the left forever. Right? It doesn't asymptotically approach anything. Just takes off. Yeah. All right. What else we got? Got uh, okay, this one here. Looks like they want us to shift this around. So let's see. P of x is the cube root of x plus 5, or how I would prefer to take this in the calculator, x plus 5, all raised to the 1/3. Okay. So the parent function, I'll put this in corner, parent function is y equals just the cube root of x or x to the 1/3. Okay, so it puts in a little dot cloud. Okay, because from that, it looks like we're just going to shift horizontally 5. And which way would this go? Well, it's +5, so that would be left, wouldn't it? Here, I'll put that up. So this would be left 5 from the parent function, which is given right here. Okay. Right, so yeah, let me just look this way. You could totally make a table of values, but I'm just gonna jump straight to my rule, and then I'll throw this in Desmos and I'll use that to see if I was right. Okay. So the parent function, I know I got 0, 0, 1, 1, because the cube root of 1 is 1. Then there's 2, 3, 4, 5, 6, 7, 8, 2. Right? If you do the cube root of 8, you get 2. Right? You could also go negative with these. So -1, -1, 2, 3, 4, 5, 6, 7, 8, somewhere way back here. So like this. Okay. Right now, here I'll just kind of dash this because this is not p of x that would have been for, but this is the parent function. Okay, so that's this guy right here, parent function. Okay. And what are we supposed to do? Go left 5. So here, go extend this. This is -8. So 1, 2, 3, 4, 5. Okay, right at the edge of my paper. Just squeeze down here. Okay. I'm gonna just shift all the points to the left 5. See what happens. Okay, so right here, right here. This would be probably right here. This goes right here. This would be right at the edge. All right. Should look like this. Okay. I'll pick a couple of test points and show you that I'm pretty sure this is correct. Right, and I'll throw that into Desmos. Okay. How about this point? How about I'm claiming, for example, that the point at -5, 0 is on my p-vax. Well, if I plug in -5, +5 would be 0. And the cube root of 0 is 0. Yeah, that's totally a point. Right? I made a little table. Right? X, Y, -5, 0. Right? Let's take another point. I'm claiming this point right here. This looks like 3, comma 2. Let's see, if I plug in 3, do I get 2? Because I just claimed I would. Okay? So let's see, if I plug in 3, 3 plus 5 is 8. The cube root of 8 is 2. Yeah, it totally is. All right, so finally, pop this into Desmos, see what that looks like. Oh yeah, there it is. That's it. Okay. Yeah, so this red one is the parent function, which you see right there, cube root of x. Right? And this blue one is, yeah, the one we've just been working on. That's totally it. Oh yeah, it worked. Yeah. All right. Next. Okay, we got example 6. Okay, we just got 2 more examples, and then I'll jump into these text questions. Example 6, compare radical functions. Okay, got p of x is, okay, the p of x shown in the graph p of x, I think what? Okay, I don't know, let's see how. So to give us a p of x is -2 times, and the cube root, I'll just do okay, x minus 6, and then I'll do 1/3 power for the cube root. Okay. Okay, the cube x shown in the graph. All right. All right, so is this p of x? That should be it. Right, well, let's see. Right. How would I think about this? So if the parent function is y equals the cube root of x, or x to the 1/3, then I think the -6 means go to the right 6, and this -2 means upside down, and stretch vertical factor of 2. Okay, that should be it. Right, so forget that. Right, so the parent, we just did a few of these. So I know 0, 0, 1, 1, because the cube root of 1 is 1. Right? The cube root of 2, 3, 4, 5, 6, 7, 8 is 2. Okay, so there's your parent right there. Of course, the cube root goes back to that. Okay, so I just dash off the parent function. Okay? Now, say we're going to go right 6. Okay, well, that brings us way over here. So if I follow this origin point from 0, 0, goes to the right 6, and then flip upside down and stretch it by a factor of 2. So upside down would go through this point and say this point or something kind of like this. Right? But then a vertical stretch of 2. Okay, well, 0 times 2 would still be 0. Right? This point should be at 5, comma 1, but times 2 would bring you to 5, comma 2. So I'm claiming the point 5, comma 2. Okay? And then this point was negative 2, 2. Right? And then times 2 would be negative 2, 4. So I'm playing this point as negative 2, comma 4. Okay. So I just claimed 3 points on the graph. This one I'll label as 6, 0. Okay. Let's see. Remember, you could have always made a table from the start. You could always do that too. So x and p of x. So I just claimed for negative 2, for 5, and for 6. Right, that's these I got labeled right here. Okay. So what if I just plug them straight into the function? Right, so negative 2 minus 6 is negative 8. 8, or negative 8 rather. The key word of that is negative 2. And negative 2 times negative 2 is 4. So it should be 4. Oh, hey, that's that point right there. Negative 2, 4. Right? Which I got originally by following all my stretch and shift rules. All right, I should go ahead and make this pink. All right, here should be my p of x, should go like that. Something like that. All right, I also claimed the point 5, 2. Let's see if that's a point. So if I plug in 5, 5 minus 6 is negative 1. The cube root of that is still negative 1. And times 2 would be positive, or negative 2, rather, would bring back to positive 2. Yeah, that is the point 5, 2. Okay? And finally, 6. Well, if you plug in 6, there's zeros out, so the whole thing zeros out. So 6, 0. Yeah. All right, and I could keep going, but yeah, that definitely matches up. Right? All right, so here, I just graphed this from two different perspectives. One is to know what the parent function is, plot those points, and then just follow all these translation rules. The other way is, well, you could just plug some x values into the original expression until you get enough points to draw the curve, right? Or you could use both methods like I just did to confirm that you did everything correctly. Yeah, it's looking like that one right there. All right, we're good. Let's see. Write a radical function. Oh, okay. So what if they give you a graph and they want you to come up with what is the expression for that graph? Right. So let's see if we can piece this together. Um, let's get some XY values right here. Right. Like I do see, it looks like the center, this looks like some kind of cube root graph. And the center point would be right here, which is at negative 3, negative 4. So the point negative 3, negative 4 is a point. Okay? I think you have to start from a parent function where the parent would be, I'll say parent is y equals the cube root of x, or x to the 1/3. Okay? Well, we got to shift to the left 3 and down 4. So we need to go left 3, down 4. Right? But that's not all. It looks like there's also a vertical stretch because I remember from the parent, if 0, 0 exists, then 1, 1 also exists because the cube root of 1 is still 1. Okay? So you could start from the origin and go up to the right 1, and that would also be a good point. But that's not actually true here. Here I go to the right 1 and then up 2. Ooh. Or to the left 1 and down 2. So I think there's also a vertical stretch of times 2, right? Times 2, maybe, right? So put that all together. Okay, I think, okay, they're calling this g of x. Now, here, keep it really generic. It'd be a times x minus h to the 1/3 plus k, right? But what are a, h, and k? Okay, well, I think it's all answered right here. So g of x should be, okay, vertical stretch 2. I'll go ahead and throw that in for a point multiplied by x. Okay. Now I said left 3, so I have to do plus 3, right? Or you could say minus negative 3 or plus 3 to get 2 going to the left. Okay. Now still raise that to 1/3 power, cube root. Okay. And then down 4, well, that means I have to subtract 4 at the end. I'm pretty sure this is the answer. Here's what I'll do is I will plug this expression into Desmos and see if it looks exactly like that, which it should. And look at there. That is it. It's exactly what it looks like. Right, so the parent function is in red and this g of x is in blue. Right, so looks like we went left 3, down 4, and also it's been stretched vertically by a factor of 2 compared to the right. Yeah, it's all there. It is all there. Now let's jump into these book puzzles then. Boom, that's it. Book puzzle time. So number 4. So this first section, they just want you to identify domain and range. I was looking at the Alex puzzles too, and there were quite a few of those. So very with it. So y equals 5 times the root of x plus 2. and then -1. Right. Okay, well, a lot of fun stuff we could do with the here. I'll throw this in Desmos too, but so domain. Let's see if I'm doing set builder notation, it would be x such that x. Right. Now, here, if I do a little math right here, x plus 2 has to be greater than or equal to 0. Right, that would be true. Okay, so you subtract over 2, x has to be greater than or equal to -2. Okay, so x greater than or equal to -2. Right, that's all. Right. So like if x was -2, then this would be 0 and it would just barely work. It would work. Right? It could be bigger, so it could be like 10. That would be fine. 10 plus 2 is square root of 12. That's okay. Right? But it can't be less than -2. Like if it was -5, you'd be taking square root of negative value. That don't work. Right, now the rate, here, let me do one more thing. Let's do set builder notation. So you could also do -2 to infinity. Do that. Okay, let's see the other way of saying that. How about the range? Well, the range, I'm thinking, uh, if this square root comes out to 0, because if x was -2, this would be 0. This whole thing would be 0. Right? You subtract 1, and that would kind of bottom out the function. So I think the range could go y such that y is greater than or equal to -1, because it's going to be bigger, just can't be anything less than -1. Or you could do -1 to infinity. Okay. So imagining that, here, sketch a real rough looking graph, and then I'll throw that into Desmos and see exactly what's going to look like. Okay. That from the parent function, yes, there's a vertical stretch, right? But most importantly for domain and range is it went left 2, down 1. So the parent function did something kind of like this. You go left 2, down 1. Now here's sort of the origin point of this actual value, right? It's still going to go kind of up and to the right, okay? Something like that. All right, so let's see, what does Desmos have to say about that? Yeah, that's exactly it. See, from this point right here, the domain, you're allowed to go to -2 and anything to the right, and the range you're allowed to start at -1 and go anything above that. Yeah, that's the point to -1 right there. Yeah, that is it. That is it. Number 12. Okay, state the domain and range, and how is it related to the parent function? Okay, so basically what we just did. Okay, number 12, right, we got y equals root x plus 4, and then -2. Okay. So I'm going to say from the parent function, but the parent is y is the root x, the little thought cloud. Okay. So relative to the parent, this is going to go left 4, down 2, and that should be it. Right? There's no stretches or anything like that. Okay. So give you guys a quick graph. Okay, so the parent basically does something like that. Okay. So if I'm going left 1, 2, 3, 4, and down 2, right? If I'm following this origin point, that would be now be down here. Okay. And now this graph is, let's see, and also throw in some other points. I think it's actually switch across to the origin, wouldn't it? Yeah, because look, watch this. If you plug in 4 right here, or sorry, 0, I meant, right? Plug in 0. This is 4. The square root of 4 is 2. 2 minus 2 is 0. It goes right through the origin. So go like that. Okay. Okay, so right, so they're looking for this right here. That could be the answer. And then domain, we could have x such that x is greater than or equal to -4, or in interval notation, -4 to infinity. Okay? And the range could go y such that y is greater than or equal to -2. Here's -4, here's -2. Okay? Or -2 to infinity. All right, there you go. That is all that. 13. Reflexes. Raquel and Ashley are testing each other's reflexes. Raquel drops a ruler from a given height, so it falls between Ashley's thumb and index finger. Hey, Ashley tries to catch it before it falls. The time in seconds to catch the ruler is given by 1/4 times the square root of the distance it falls in inches. Hey, that sounds like the extra credit assignment I gave you guys back in the day. You guys remember you paired up with friends, right? You held the ruler, you dropped the ruler, and caught as fast as you could. Depending on how far the ruler fell, you could calculate how much time it was falling for, therefore your reaction time. Now, I was having you guys use metric and centimeters because that's what I do in my physics class. You're going to inches, but okay, you can come up with an expression for that because they told you exactly how to do it. Now, they said the time to catch the ruler, time, is equal to The product of, so something, product of, that means you're multiplying something together, okay? 1/4, so 1/4, and the square root of the distance it falls in inches. So the square root of, well, how about D? D for distance. That could be it. Yeah. Okay. As long as distance follows in inches and times and seconds, should be pretty close to the value, right? Write a graph of function. Oh, they also with D for distance, right? And T for time. Describe the key features. And okay, let's see this. Okay. So we come with this. This. Okay. So okay. Distance in inches and time in seconds. Okay, something like that. Okay. Well, most students are able to catch the ruler. The ruler only goes up to about 12 inches. So I bet if we scale this to like 10, that should probably be pretty good, right? So 2, 4, 6, 8, 10. Right, so here, 2, 4, 6, 8, 10. Almost everybody can catch it within about 10 inches now, right? So, right. And then, what else here? Uh, Time. Well, I bet reaction time is like a fraction of a second. So here, let's plug in the biggest value I have here, 10 inches. Okay, and let's see what it comes out to. So 1/4 of the square root of 10 would be 0.8 second, or 0.79. I'll call that 0.8. Okay. So let's go, see, is that right? Huh, okay. Um, 0.2, 0.4, 0.4, 0.6, 0.8. So 0, 0.2, 0.4, 0.6, 0.8. Okay. Again, notice that here, I really want to emphasize this. Okay, is notice how both my axes start at 0, so 0, 0, okay, and are scaled linearly. Okay, so for distance, 0, 2, 4, 6, 8, 10, and for time, 0.2, 0.4, 0.6, 0.8. Okay, is it? Okay. So that when I plot the points, it actually should create a square root curve. Okay, let's see if it does. Um, in the real world, I bet you're going to have to make some graphs at some point in life, and you might have to also adjust the axes accordingly so that it fits nicely on the page. You can base what information you're trying to convey. Right? So let's go 0, 2, 4, 6, 8, 10, right? And then time. So 0.25 times 0 to the zero point 0.5. Guys, power 0.5, that could also be square root, same thing. So 0, 0 is a point. If I plug in 2, I get 0.35. I don't think this equation is exactly accurate now that I'm looking at it. Did they really say that? Product of report? Yeah. Okay. Right. Okay. I'm really being academic with this, just following this straight out of the book because I don't think this is super accurate. But just get the idea. Like okay, 0. Yeah. Okay. Sorry. 0.61. 0.71 and 0.79. Right. Yeah. Really tempted to go off on a tangent. But here, if you want to know a more accurate version of this, just think back to when I had you guys do this activity or take my physics class. Right. Be a lot more accurate here. So 0, 0, right, 2.35, 4.5, 6.61, 8.71, 10.79. Yeah, look at there's. That's a nice square root looking graph. Oh yeah. Oh yeah. 14. Consider g of x. Here's g of x. Identify the transformation. Okay, how is this transformed? Okay. Well, this looks a lot like parent function square root of x, except shifted to the right. 1, 2, 3, 4, 5. I think that's all. Because look at this. 0, 0 is a point, and 1, 1 would be a point on the parent function. And if you start at 0, 0 and go to the right one F1, it also lands on the function. Right, and then how about square root? 1, 2, 3, 4, 2. Yeah, I think that's all it is. Now I'm looking at it. I think g of x is just the parent function f of x, which would be the square root of x. Okay, and then shifted to the right 5. So how do you go right 5? Well, I'm going to extend the square root and just say -5. And I think that's it. I think that should be the entire thing. Okay? Now to super confirm that, I'll check the values against this table. So we're going square root of, uh, hang on a minute, how did consider g of x? That does not look like the same. What are they doing here? That's not a point graph. Well, okay. I think this is a different question. Why are these two? This go to 15? Maybe this goes to 15. No, I don't know what this is. Gee, that's okay. I don't know. All right, but that's how you do that. Okay, so here, just move on here. Number 17. Graph each function, state the domain and range. Okay, now we're doing cube roots. Okay, so we got f of x is 3 times, okay, then the cube root of x minus 2. So I'll write x minus 2, and then power 1/3, guess that would be a cube root. Okay, well, if the parent is y equals x to the 1/3, well, dot product, okay, then relative to that parent function, this will go to the right 2, right, and then vertical stretch factor of 3. Right. And yeah, I think that's the whole thing. Right, so get some axes. Let's go x, y. Okay. Now right here, I want to leave some space to the right. See if I can scale this to about 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I need to go up to there. Okay. And for the y-axis, I think I would just go up to 3, down to -3. That should. Oh no 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 no! We got a vertical stretch of 3. Let's go 369. 369. That'll be much better. Okay, I'll throw my. Okay. No, actually, you know what? These are kind of these axes are kind of scaled the same here. Work out. Okay, so yeah, I can also, of course, make a table on the side. Consider that x, and let's go f of x, which would be this full transform. Okay. So I know the parent function cube root of 0 is 0, cube root of 1 is 1, cube root of 8 is 2. Okay. So I'm going to kind of dash this. You can also go negative with that. It creates this kind of looking graph right here, something like that. Okay. Okay. Now, relative to that, I said, let's go to the right 2 and then stretch the whole thing vertically by a factor of 3. So to the right 2, we take the 0, 0 point and put it right here at the point 2, comma 0. That's right 2. Okay. What about 1, 1? Well, that also goes right too, but then it gets vertically stretched 3. That's the point. Now it's at 3, 3. Okay. Now there was also a point originally at 8, 2. So shift to the right 2, brings it to 10, 2, and then times 3. 2 times 3, 6. It should be right here at 10, 6. Okay. How about the other way? -1 was a point, right 2 times 3 should be this point right here at 1 comma -3. There's also -8, -2. So shift to the right, we get to -6. And -2 times 3 is -6. I'm pretty sure this point at -6, -6 exists. Okay. Now, I just made all those by considering these translation rules. Right? That's how I came up with these 5 points right here. So I'm pretty sure that the graph should look like this. Okay. But what if I had used this table instead? Okay. Calculator time. I'm going to test all these 5 points right here. So I'm claiming that at -6, 1, 2, 3, and 10, these should all come out to integer values. Let's see if that's true. So 3 times. Okay. Here, I'm going to try that trick I've been showing you guys. So I'll put answer in for x. I'll say -2, power of, and then parentheses 1/3. Okay. All right. So then type -6, scroll up, plug it in where that answer was, and come on, I should get -6. Let's see. And I do! Oh yeah! Type 1, plug that in. I should get -3. Oh yeah! Type in 2, scroll up, I should get 0. Oh yeah! Type in 3, I should get 3. There's 3, 3. Oh yeah! And finally 10, scroll up, plug that in. I should get 6. Let's see if I do. Oh yeah! 5 for 5. Math is winning. Yes. Number 21. Ooh, write a radical for each graph. Radical function, right? Well, this number 21 does look like a cube root. It looks like it's been shifted to the right two up one. So right two up one. Okay? Now, relative to that, if that's like was the 0, 0 point, now right two up one. I know it can go right one up one on the parent function and get another point. And this one also hits that one. So what I'm trying to get is there's no vertical stretch or anything like that. This is just a straight shift. So if let's say f of x was like the cube root of x, right? Then g of x, I'll just call this guy g of x, would be that function right two up one. So right two would be like x plus two. No, it isn't. It's x minus two. See, that's the non-intuitive one. You got me. You got me. Right, so x minus two, right, raised to the 1/3. And then up one, I'll do plus one. Okay. That should be it right there. Right. So here I'll check a few points and I'll see if it aligns with that graph. Right? Like I do see here 3 points that stand out to me are the point 2, 1, of course. So 2, comma 1, 3, comma 2, and also 1, comma 0. Right? Now, does this function I just wrote agree with this table of values? Well, if I plug in 2, this zeroes out and I get 1. Yeah. If I plug in 3, 3 minus 2 is 1, cube root of 1 is 1, plus 1 is 2. If I plug in 1, ooh, I get negative 1 here, cube root is still negative, and plus 1 would be 0. Yeah, all these are working out. Right, keep going, but fair enough. Okay, number 31. Ooh, inequality. You guys remember inequalities? Hey, if y is greater than or less than, right there. Yeah, right. So y is less than or equal to 6 minus 3 times the square root of x minus 4. Okay. Here. One thing I'm going to do right away is rearrange this a little bit. Okay, so could this be this negative 3 times the root x minus 4? And then tag on the plus 6 at the end. So you do that. Okay. So relative to the parent function, so if the parent function is y is the root x, so you basically square root looking shape. All right, both out here. This would go right, yeah, right for this would be upside down stretch vertical factor 3, and then up 6. Okay, so all those things would be true. Okay. Now keep in mind, we're also going to shade part of this graph. So we've got to draw the graph first as if it was equal to, and then say, well, actually, it could be less than that. Right? So all that would be true. Um, oh, you know what? If we start with the square root, which basically does this, right? So 0, 0, 1, 1, 2, 3, 4, 2, and then 5, 6, 7, 8, 9, 3, because square root 9 is 3. Okay, so here's your parent function right here. Here's the parent. Okay, okay. We're going right 4, up 6, and then upside down. Okay, so I think it's going to be like really big over here. Okay, so right 4, okay, if I just follow the 0, 0 point, 1, 2, 3, 4, there's right 4. Well, here, I mean, maybe just a little backwards, but this will make sense. If I shift it up first, I shift it way up, okay, I can still flip it upside down after the fact. I just don't want to mirror this way. I just want to flip it over this point that itself is shifting around. 3, 4, 5, 6 is up here. So that move it right here. Okay. And then it's going to come down. It's going to shift upside down like this. Okay. So this is the point, say 4, comma 6. 4, comma 6 is right here. Okay. Then, see, I did have the point 1, 1. Okay. So that also shifts to the right 4 and up 6. Okay. Which brings 7. Okay. But then flip that upside down. Then stretch factor 3. 1, 2, 3. Should be right here. Okay. Let's look like 5, comma 3. Okay. Okay. And there's also the point 9. Well, okay, that's way up there now. Let's do the point 4 comma 2, right? I think that'll fit nicely here. Okay. So right 4 brings us to 8. Here's 8. And now it's over here. Okay. Up 6 from 2 brings it up to plus 8. 1, 2, 3, 4, 5, 6, 7, 8. It's way up here. So this would be the point 88 is way up here. Right. Then relative to this original point, it's 2 up. So when I flip it upside down, it's going to be 2 down from there. So it's 0.34, or sorry, 884. Right, and then stretch 3, that's 1, 2, 3. That'd be back at 0. Yeah, I think the 0.80 exists. Okay. Uh, 80. Right. All right, so I just put those points together logically using all my translation rules. Okay. But let's see that passes the table test. Right, so xy for this function right here. Okay. So I got some points. Got some x coordinates of 4, 5, and 8. And I'm claiming that the y value should be 6, 3, and 0. Right, so let's see if that's true. So 6 minus 3 times the square root of x minus 4. Let's do 4 minus 4. Okay. Yep, that's 6. And then if I plug in 5, I get 3. Yeah, 4, 6, 5, 3. 4, 6, 5, 3. And finally, 8, 0 should be a point. Let's see if that's true. Yeah, it totally is. Yeah, so it totally worked. All the translation rules. Okay. So I did translation to make that curve. I checked with the table. You could, of course, always make the table first and then just plot a bunch of points. The curve will naturally emerge anyway. Yeah. One more thing. I almost forgot. Y is allowed to be less than or equal to that expression. Right? Yeah, we gotta shade this. So less than or equal to. Well, there is a domain restriction, right? So x cannot be anything less than 4. X is allowed to be 4 or bigger. And then y value is allowed to be anything less than this. So I need to hatch in all this right here. And on it goes. Right, so I'm hatching in all this right here. Right, there you go. So there's your full inequality. Yeah. All right, a few more here. We got La Riz is standing at the side of a road watching a cyclist. The distance in feet between La Riz and the cyclist is a function of time is given by the square root of, so 36. So the distance, I'll say d, distance in feet, is given as a function. The square root of, so square root of something. The sum of 9 and, so sum of 9 and, the product of 36 and the times squared. That's interesting. Right? You know what? I think I could manipulate this a little bit. Okay, so I'm gonna write this a few different ways. I could do this with it. I could go 36t squared plus 9. All that right from I do see a 36 and 9. I could factor that out. Or I could factor a 9 out, I should say. This would be 4t squared plus 1. Right? And then, well, the square root of 9 itself is 3. Okay. So these are all different ways to think of the exact same function. Like if I graphed all 4 of these in Desmos, they would all be the same graph, is what I'm saying. Okay. So what does it want us to do here? Write and graph a function where t is the time in seconds and d is the distance in feet. Okay, well, got the function written. It could be any of these. Just pick your favorite. Okay. I kind of like this last one. Let's go with that. Okay. So let's make a table of values. Okay. Now, this one's a little tricky because there is a factor of 4 on that t. So maybe what I'll do is I'll just allow decimals and come up with different values. Okay? So time and distance. Now, I suppose there's some reasonable times. Let's go time 0, about 1 second. Let's go 5 seconds, 10 seconds, 15, and 20. That's probably plenty of times, right? We'll go 20 seconds. Okay. Okay, so then here, I'll just feed all these values in here. I'll get some decimal answer. I'll round it a little bit. So 3 times the square root of 4 times, I'll say answer squared. Answer will stand for t. And then plus 1. That's all under the radical. Then I'll plug in 0 and get 3. Okay, yeah, times 0. 3 times 1 would be 3. You'd be 3 feet away at times 0. What if I plug in 1? I get 6.7. How about how about if I plug in 5? Get 30.15. About 10. 60. I should really just learn about that. 15 seconds, get 90.0. And 20 seconds. 120. Interesting. Point oh. Hmm. Hmm. Okay, and then let's make a graph out of this. Graph time. So let's put time in seconds on this axis. Now, I just went up to 20 seconds, so I'll go ahead and scale the graph like that. Let's go 5, 10, 15, 20. So 0, 5, 10, 15, 20. And the distance maxes out on 20 feet. Okay, so distance in feet. Let's go 20, 40, 60, 80, 100, 120. 0, 20, 40, 60, 80, 100, 120. Ah, let's get some points. So 0, 3, 1, 6.7. Right there. 5, 30, 10, 60, 15, 90. And 2120. You know what? Okay, I see. Okay, that confused me at first, but you sure read this correctly. Yeah, okay. I don't know why I didn't catch this right away. You guys notice how we're taking the square root of times squared? Okay. It doesn't exactly cancel out because you are adding more under that radical, right? So, so you can't really simplify it so much beyond this, right? But it's sort of, in terms of the graph shape, has a cancellation effect. Maybe it's sort of asymptotically approaches something linear, right? So this curve is not exactly linear. I can't properly hold my ruler and zip off a straight line, right? But I think this asymptotically approaches a straight line. In fact, kind of looks like a straight line, right? Very close to a straight line. Okay, so that's interesting. Describe the key features of the function. So I think what they're looking for is things like the domain could be uh, time such that time is greater than or equal to 0 seconds. Range could be distance such that distance is greater than or equal to, well, at time 0, you were 3 feet away. So it's got to be at least 3 feet away. And it just grows from there. Okay. You could say as time approaches infinity, distance approaches infinity. That'd be that in behavior. Okay. Okay, it's always increasing left to right. Okay, so all those would be. 37. Geometry, the length and radius of a hemisphere can be found using this expression in terms of volume. Yeah, here's a good formula to know. Here, I'm just giving this as bonus. Volume of a sphere could be 4/3 pi radius cubed. So if you have a little picture, like the equator, some radius r. Okay, so got all that going on. Okay. Well, what if you solve for radius in terms of the volume? Well, let's do that. So multiply both sides by 3/4. So pi r cubed equals 3/4v. Right? Divide both sides by pi and then take the cube root. So radius is the cube root of 3/4 pi and then times v. Right? Or if you like, radius is 3/4 pi and then v all raised to the 1/3. Okay. Is that what they told us? Yep. No. Did they mess this up? This looks a little different. Well, why did they put 2 pi down here? I don't know. Okay, let's go with that. Oh, I see why. Because we're talking about a hemisphere. Okay, that's what it is. I did the full sphere. When they say hemisphere, they're looking at just half of this. If you cut those in half. Okay, that's why they got it too. Okay. Anyway, it's the same basic shape though. Right, so however you think of it. Okay, so you could make an XY table. You could say, what are the different volumes of these either spheres, in my case, or hemispheres, you might buy the book. Okay. What's the corresponding radius? Okay. Maybe if you had like a bowl of water, you filled it up with water, and then you measured the water. Okay. That could get you different volumes. Say, I wonder what's the radius of my bowl? You could think of it that way. Okay, so well, this is going to be a cube root function here. So you could totally make a VR table. You can plug in lots of values for V, plug in the calculator, get lots of values of R. But you guys know the basic shape because you've seen it over and over and over. It's going to be a cube root shape. Okay. So the radius is proportional to V to the 1/3. I mean, it's going to make that shape, right? Right. Um, and last one, 43, create, write an equation of a relation that contains a radical and its inverse such that the original relation is a function, but its inverse is not. And then vice versa. The original relation is not a function and the inverse is. Okay? Right, so I know a real good example. I'm sure there's a lot of examples. It's one you're supposed to be a bit creative with this. Right? But one I know right away is how about f of x equals x squared? Right? So if you make a table of values, x, y, if x is -2, -1, 0, 1, 2. Well, if you square all those, you get 4, 1, 0, 1, 4. Okay. So 0, 0 is a point, 1, 1, 2, 4, -1, 1, -2, 4. Okay. So there is the original function. Right? But what about its inverse? Ooh, you guys remember? Because this is also a review of what does inverse mean? Okay? So a couple of interpretations. One is that you could just switch the x and the y. Right? So I could say instead of y equals x squared, you could, I'll spell it inverse. Get really obvious one bit. You could say x equals y squared, and then rearrange this. Therefore, y is now you could say square root of x, but be careful. If you just see this on a page, usually it's implied that you're only working with the top half. Okay? But if you have y squared is equal to something and you take the square root yourself, uh, usually it is expected that you also include the plus or minus. That's what would make this one not a function because the square root of x got 0, 0, 1, 1, but also 4, 2 could be a point. Ooh, now it's starting to look like more like this. Okay. And then how about negative? You could also have, wait, if there's a plus or minus side of this. Okay. This is what f inverse x looks like. Right? I guess that right? This would not be a function because it would fail the vertical line test is one way to say it. Right? Now, something else you might remember about inverse functions, like graphically, is that they're sort of reflected over this y equals x line. Right? And just dashed off right there in blue. Okay? So if you pick up your paper and you flip this graph over the paper, okay, then these two relations will swap places. Okay, so see if you can see through the paper. Okay, yeah, you can kind of see through the paper there. Okay. I'll make these really dark. Make these really dark. Okay, so this one, so it'll show through the paper easier. I think I had a marker up here the other day, but that was make it really bold pen. Okay. Okay, so there's the original function, which is now heavy black, and here's the inverse function, this heavy pink. Pretty close to what this would look like. Okay. Let's see if this shows up through the paper better. So that pink and that black should swap places. Okay, yeah, that's a little more obvious now. Yeah, they totally did. Okay. That's another way you can get inverse. Okay. All right. So that is a wrap on 6.5.